Hello everyone, in this theoretical tutorial number 64, the main target is to analyze the gain of a dual-stage amplifier with no capacitive load. To find the total gain, we will calculate the second stage gain and its input impedance. The first stage gain will be calculated by using the second stage input impedance as the load of the first stage. We will start by calculating the gain of the common source amplifier using NMOS, a resistor load RL, and a capacitor C between drain and gate. This diagram shows a small signal circuit with a transconductance GM2. To plot the gain versus frequency of this amplifier, we will start by the DC gain equal to GM2 times RL. This DC gain asymptote will stop when the angular frequency is equal to 1 over RLC. A simplified small signal is plotted showing only the resistor RL as a load. When the angular frequency is higher than the pole 1 over RLC, the majority of the GM2 V in current will flow in the capacitor C, so the gain will decrease versus frequency with the equation GM2 over JC omega. A simplified small signal is plotted over, showing only the capacitor C as a load. When the angular frequency is higher than GM2 over C, the capacitor C behaves as a short circuit, as shown in the simplified small signal plotted over with a red line represented the capacitor C shorted. Due to the short, V in equal V out, so the gain is clamped to 1 or 0 dB. After plotting the gain, it is time to analyze and plot the input impedance of this circuit noted Z in. At low frequency, the impedance is capacitive. The input capacitance C in is equal to the capacitor C multiplied by the voltage gain GM2RL plus 1. Of course, as this capacitance depends on the DC gain, the capacitive input impedance stops when the angular frequency is equal to 1 over RLC. When all the GM2V in current comes from the input through the capacitor C, the input impedance becomes resistive and equal to 1 over GM2. So, when the angular frequency is lower than 1 over RLC, the input impedance is capacitive, and when the angular frequency is higher than 1 over RLC, the input impedance is resistive. Now it is time to add another stage driving the existing one. The added stage becomes the first stage and the other the second stage. We can plot the DC gain of the first stage equal to GM1 times R. When all the GMI times V in current flows in the resistor R. But we saw that the second stage provides at low frequency a capacitive input impedance equal to C in. So when the angular frequency is higher than 1 over RC in, the majority of the GM1 times V in current flows in the capacitor C in. The gain becomes equal to GM1 over JC in omega. This gain decreases until we reach the angular frequency 1 over RLC. At this angular frequency, the input impedance of the second stage becomes resistive with an impedance equal to 1 over GM2. Then we have again a constant gain equal to GM1 times 1 over GM2. Now we have both gain curves. The black curve is the gain Vx over Vin of the first stage, taking into account the input impedance of the second stage, and the blue curve is the gain V out over Vx of the second stage. Of course, the total gain of both stages is the multiplication of both gains. The dark blue arrow represents the DC gain of the first stage of 20 dB. By adding this arrow over the second stage gain, we will get the total DC gain plotted in red and equal to GM1, GM2, RL. By multiplying both black and blue curves between 1 over RC in and 1 over RLC, we will get the gain GM1 over JC in omega times GM2 RL. Since C in can be replaced by GM2 RLC, after simplification we obtain the gain GM1 over JC omega. Then, by multiplying black and blue curves between 1 over RLC and GM2 over C, we will get the gain GM2 over JC omega times GM1 over GM2. By simplifying with removing both GM2 on numerator and denominator, we will get the gain GM1 over JC omega. Of course, for angular frequency GM1 over C, the gain is equal to 1. Finally, when the angular frequency is greater than GM2 over C, multiplying the two gain curves, the blue one with a gain of 1 and the black one with a gain of GM1 over GM2, we will obtain the total gain of both stages and represented with a red curve. In summary, we can keep in mind that when the dual stage gain is lower than the DC gain equal to GM1, GM2, RL, the gain will be given by the transconductance of the first stage, GM1, times the impedance of C, which is the Miller capacitor. Then, at high frequency, when we can consider C as a short, the gain is equal to GM1 times the constant input impedance 1 over GM2 to give a constant gain of GM1 over GM2. I want to thank you for your attention. After reviewed the dual stage amplifier without any capacitive load, on my next ERICR tutorial number 65, we will see the dual stage amplifier with the effect of the capacitive load on the second stage. So see you soon and stay tuned.